Hello and welcome to the final microprocessor demo. We have our expanded ALU test right here. We have our input in hexadecimal, output also in hexadecimal, but I also have the input in binary and the output in signed decimal and binary to show the output in different formats for visibility and simple understanding. We got 8 modes here, including the default 4, subtract, add, multiply least significant, and multiply most significant. The 4 that I added are shift left, shift right, rotate left, and rotate right. Shifting is just moving all the binary digits over to the left or right. Rotating is the same thing, but any digits that are falling off the side will be wrapped around and brought to the other side. And we will be cycling through all of these modes to demonstrate that the circuit works. So right now we already have 2 and 2 as our A and B input, and select is set to 0, and the output is obviously 0 because 2 minus 2 is 0. And if we set the select to 1, it's going to be 4 because 2 plus 2 is 4. Now multiplication is a 2-step process. First we set our select to 2, and 2 times 2 is going to equal 4. But if you're doing multiplication with larger numbers, you're going to need to also do it with 3. In this case it equals 0, but if you had a larger number, you'd have the most significant bits, and you would add that to your least significant bits. So in this case, 2 times 2 is 4, and then you add 4 to 0 because the most significant bits are still 0. You're still going to get 4. Now let's move on to mode 4, which is a shift left. So our input is 2, and the amount we're going to shift it is 2. So if you look here, the 1 is the second bit from the right, and now it's the leftmost bit because it was shifted over to left 2. Now when we use 5, it's actually going to be all zeros because it's shifted right to the 2, which is going to cause that 1 to fall off and be lost. Now if we do rotate left, it's going to be the same exact thing as shift left in this case. And rotate right is like shift right, but now that bit that fall off is going to wrap around to the left side. So this is the inside of the ALU. As you can see, the 4 functions are added: shift left, shift right, rotate left, rotate right, and I'm just duplicating this already existing ALU mini, and I just added an extra mux that will switch by setting that to 1. It will switch to this area, and there's 3 muxes here, and the reason I chose mostly just shifters and rotators is because it's kind of elegant in a way, and you'll see in a second. So with this set to 1, it's going to default to shift left, and you click this to change it to shift right. Or you can change this to change it from shifting to rotation. And then, so you could do, shift left, shift right, rotate right. That's why I chose it, because this mux switches it from shifting to rotating, or this pin does it, and this pin changes it from left to right. I mean, as long as this is 1. If it's 0, then it's switching to all this default behavior for the minus, plus, and multiplication. Okay, so if A is 1 and B is 0, when we're shifting, nothing's going to happen. B is going to be the shift amount, which can only be 2 digits, so these first 2 digits are completely cut off, they don't do anything. These second 2 digits is what going to determine how much you shift, so we can shift it 1, and you'll see it's shifted to left 1. That's shifted 2, that's shifted 3. You can change it to be shift to the right, and it's going to go off. We can change it to rotate, it's going to be the same until we shift it right, and then it will be shifted 1, be rotated, shifted 2, shifted 3, and that's that. Okay, so why is it useful to have this expanded ALU at the center of our microprocessor? I'd say it's because it adds a small layer for abstraction. It's kind of like, a calculator with functions that this whole controller circuit can use, instead of this being, unraveled, and each component of this circuit is all over the place. It's a lot more simple to have. We want to use this function on this piece of data, and then use this function on this piece of data, rather than having to manage with the mess that would be, loading this data, and it would be loaded into all these different places, and then trying to figure out which operation to perform at what time. It would be very complex, and this simplifies it a lot more. And it's really good for developing and testing because you can test the ALU on its own manually, and then you plug in the ALU to this bigger circuit, or you make this larger circuit around the ALU, and you can test that because you know the ALU works, and you can test if the controllers work. So it puts things in boxes, which makes it a lot simpler to have these little building blocks rather than have everything expanded and, hard to be able to manage and piece together. So I think that's it for this video. Thank you for watching.